If you're looking for a content explaining what is sampling and having best practices, then this episode is for you. Welcome back to the Is It Observable YouTube channel. Today's episode is going to be part of the OpenTelemetry series where we covered quite a lot of episodes. When we start jumping into the beautiful world of OpenTelemetry, we usually get very excited as soon as we start seeing our first spans, or trace, and metrics and logs in our Observability backend. We then spend time understanding the quality of our data produced, and in the case of traces, we try to see if the auto-instrumentation produce useful spans. And then we fine-tune our trace by adding potentially manual instrumentation. All this to get a beautiful painting of our system. I like to compare observability to art, where we give you tools, in case tools here is going to be OpenTelemetry with the SDK, and then we can then start illustrating our application's behavior with those tools. Usually, once we have our first data, we leave some time to see if our trace or metrics or logs help our team to understand issues during QA or production. However, there is another crucial aspect to consider, and it's sampling. In today's episode, we'll try to explain the various sampling techniques and share some best practices. If you enjoyed today's content, don't forget to like and subscribe to the channel. So let's see what you're going to learn out of this episode. We'll start by reminding the various type of sampling decisions available in OpenTelemetry, but also used by our observability vendors. We'll then focus on head sampling and then the various sampling available in the collector. Last, we share some best practices, specifically if you use tail sampling, and then we need to keep track on our sampling efforts, so I'll share some tips of type of metric that we should pay attention to. Sampling is a very important and difficult point to define. Before OpenTelemetry, vendors went through the journey of building their agents or SDK producing telemetry data. Due to the nature of the data, each vendor quickly realized that the volume of data is huge and we need to store only the useful information that will help us to reach the golden goal of observability. In fact, at that time it was mainly named monitoring, so we were trying at the time to report health. And also, do we have enough data to start troubleshooting an issue in production? The tooling have, of course, changed over time, but with my performance engineering background, I can share that the level of details provided has significantly changed over time. In the past, performance engineers used to never use production monitoring tools during tests because the granularity of the data was too big in old production environments. I mean, one data point every 30 seconds or even minutes. To report health, it is enough, but to understand in details performance problems, it is clearly not enough. Trying to report a performance behavior with such data, you end up looking at averages of averages, meaning you are losing any potential spikes that may have happened during that 30 seconds time frame, for example. That is the reason QA performance tools were collecting data usually every seconds, and we also had these options to keep the raw data. Of course, the size of the results files were huge due to the number of data collected during the test. This highlights the importance of sampling and, moreover, how much data that we need depending on the role. At that time, we were mainly relying on metrics. There were few solutions at that time that was already providing distributed tracing. But now, with OpenTelemetry, the usage of distributed tracing has significantly increased in many organizations. And the big downside of this is that sampling is now in the hands of the end users. In the past, vendors defined their own proprietary protocols to report telemetry data between the agents and their solutions, but also to control the agents from the main server. With this type of design, vendor had the options to create what we call adaptive sampling, where the server will set a rate limit on the spans. This limits, of course, depends on the license of the customer. Adaptive sampling means that the local agents will identify each spans depending on its volume. It is able to classify on a given service the spans in different buckets. So we have the low usage service or endpoints, the medium usage service or endpoints, and last, the highly used services or endpoints within that services. The sampling decision will be dependent on the usage and also report consistent data. To report consistent data, the vendor solution usually add in the trace context details about the sampling decisions made by the agents. Of course, if the vendor had a feature allowing the user or the end user to mark a given request as a key request or important endpoint, then this flag will be considered in the sampling decisions. Dynamic or adaptive sampling is the holy grail of sampling decisions because the end user does not have to configure anything. He will get the right level of data depending on the actual situation. If you use simple sampling techniques, you end up making decisions on not precise information. For example, let's say I have a bag of 100 marbles with 10 different colors. And if I decide to only pick 10 marbles out of that bag, and then I look at them and I say, okay, I have 5 reds, 2 blue, 1 yellow, and 1 white. So with this sampling, I will say, okay, there's 50% of marbles that are red, 20% blue, 10% yellow, and 10% white. But does it really represent the situation? No. That is why sampling is so important. There are various other types of sampling that we rely on when instrumenting our applications. We can split, in fact, those sampling decisions in 2 distinguished families. The head sampling, meaning that each component, each service will sample at the source. So if you have an application with 5 services, each services will sample their spans differently. And then we have what we call tail sampling. That means that we need to send our spans to a central component. And in the case of OpenTelemetry, this component will be the OpenTelemetry collector. The collector will apply the right sampling decision based on a set of rules after receiving all the spans of a trace. So tail sampling is by far the most precise sampling decisions, allowing us to control the volume without losing any details. I mean, if we had adaptive and consistent sampling, then no question. I mean, head sampling will be clearly precise as well. But tail sampling, as of now, in OpenTelemetry, is the best solution. So OpenTelemetry offers various head sampler that would need to configure directly on each SDK. This could be either defined in various ways, so depending on the SDK that you're using. So there's the first option is a code snippet like this. So basically you define your trace provider, and within the trace provider option, you can define the type of sampler that you would like to use. We can otherwise define it with using global environment variables of OpenTelemetry. So there's plenty of them. So here, for example, I'm using the auto trace sample, and here I'm precising the type of sampler that I want to use. And of course I configure, in the case of here trace ID ratio, the argument, which is 0.5. And last, recently, the OpenTelemetry project allows us to load a configuration file that will configure the SDK once the app is loaded. So here is, for example, the URL to the repo with this configuration file. And here is an example using a configuration file to configure the SDK. So as a result, this is currently mean that we need to define the head sampling before the actual start of our application. Anyway, what type of sampling decisions do we have at the SDK level? Let's cover them one by one and see the potential limitations of each different sampler. So the first one is always on. So always on is meaning 100% of the spans will be sent to our Observability backend. 100% of traces is not ideal because it may impact the network to transport all this data. And moreover, this is going to be stored, so the cost of storage and potential licenses used on the backend. We have the clear opposite with always off, so it's going to be 0%, meaning no details, nothing, completely blind. Then we have trace ID ratio, so we will need to define at the component level a ratio, determine how much spans we would like to sample on this given service. For example, if I set 0.1, it will mean that 10% of the spans produced will be exported from that specific services. Then we have parent-based. The sampling decision will only keep the spans if they have a parent span ID defined in this trace context. The sampling decision is perfect if you want to drop any asynchronous process that are not involved in an end-to-end transaction. So we could clearly combine trace ID ratio on the root span to limit a specific number of spans, and then use parent-based so all the dependencies will be sampled. There's even also sampling that combines different sampling decisions we discussed. So the parent-based trace ID ratio that combines both sampling decisions. So parent-based plus trace ID ratio. But the major issue behind trace ID ratio is that OpenTelemetry is currently adding a flag in the trace context to notify the child that it has been sampled. So all the other services will sample based on this field. But the major issue is when a trace comes in the Observability backend. I mean, nothing is currently holding the actual ratio defined at the given level. So the Observability solution usually looks at the spans, and from the spans it produces stats like the error rates, the response times, the throughput from the collected spans. But we have no clue on how precise this metric has been built. Again, if you're only looking at the average of 1% of the traffic, then we are not really looking at the real behavior of our services. From a business transaction perspective, there are spans that would be present in every call and other that will be triggered for specific use case. Defining a fixed ratio without considering the usage, the volume of each endpoint, it is not helping us to get all the details that we need. So it would be awesome to be able to set different ratio based on the usage of the span, similar to what we discussed with adaptive sampling. Out of this, the big problem, like mentioned before, is not having the details stored in the current ratio used on the span. This information would improve the analytics done based on traces. The great news is that there is a current initiative trying to resolve this challenge through consistent sampling. A colleague of mine, Otmar Erdl, made a great comparison to highlight the potential issue. So let's compare distributed tracing with a running race, like a marathon, where we have many runners, and during this race we have real persons or physical persons that will record the timestamps of the runners at different stages of the race. Let's say we have different stages, A, B, C. Keeping track on all the records end up having too much data to keep up with, so we will need to sample. So if A measure only 20% of the runners, B 30% and C 10%, we'll end up with a sampling rates of 0.20 multiplied by 0.30 multiplied by 0.10, and that will return 0.6% of the runners. So at the end with this, we are very far from having a meaningful statistics. Every runner in this race has a number, an ID, and it's the bib. The bib actually has the number of the runner. So let's say now that we will use this data to sample. So A picked 20% of the numbers that are under 300. B, 30% of the runners that has a number under 400. And C, 10% of the runners having a number under 500. And this result is now different. This result is the minimum of 20, 30, and 10, and it's going to end up with 10%. So at the end, with this approach, we have more precise. We have 10% of samples compared to the other one that had less than 1%. This approach is named consistent sampling to get better statistics, and in the case of distributed tracing, the initiative is adding details in the trace context to be able to produce precise statistics on the data ingested in the backend. Consistent sampling decision is not globally available in all the language, but it is currently only available in few language in experimental mode. And this is going to be for Java and for Go. So let's hope that they will be implemented in more languages and stabilized so we can take advantage in our sampling decision. Consistent sampling is going to use this notion of ID that we took as an example of the runners, meaning that it stores two values in a trace context. We have P and R encoded in 56 bytes. The purpose is to keep track on each decision made in the entire trace. And the ratio is not set on the current traffic, but on the idea of the traces, making it more precise, like explained with a runner example. In the W3C trace context, we have a trace parent. So here's an example. So you see there's a field trace parent with some details, and then we have a trace state. The trace parent field contains the version, the trace ID, and the parent span ID. And the last digit, 01, means sampled. Trace state will hold a vendor field named OT, having two values. The first proposal is currently using two fields, P and R. It seems that it will be replaced by other fields to allow arbitrary sampling probabilities. The new fields would be TH and RV. P holds the ratio of the span, and R is a shared random value to propagate the value within the entire trace. So the root span generates a random value R, and this value will be propagated into the other spans. And a span is sampled if the value R is greater or equal to P. So let's look at our example that we had a few minutes ago. In our example, we have 3 and we have 2. 3 is obviously bigger than 2, so it means that it's sampled. So what does the value mean? R and P needs to be between 1 and 62. P is the probability expressed, so it's going to be 2 exponential minus R, or P. So in our case, it's 2 exponential minus 2, so it's 25%. To get the value of R, of our random value, it's going to be a calculation. So it's 2 exponential minus R plus 1. This approach is smart to improve our statistics and define more consistent sampling in our environments and within our trace. So let's keep an eye on this initiative because it will significantly improve the future of head sampling. The OTel collector has 2 processors for sampling. We have the probabilistic sampling and the tail sampling. Probabilistic sampling applies a logic described in the consistent sampling to have a more consistent sampling applied with a defined percentage. What is exciting with this processor, so probabilistic sampling, is that it is not limited to traces. It can also cover logs. The objective is to sample the data based on a sampling percentage and consider the sampling priority that we could hold in our spans or within our logs. In the case of logs, we can configure the attribute holding the sampling priority, so we can customize at the end the processor. The probabilistic sampling had 3 modes, so we have hash seed, proportional, which is a default mode, and then equalizing. So here is the difference between each node. Hash seed has the advantage to provide a specific feature for logs that may not have any trace ID at the end. Hash seed has the option to define another attribute that could be considered to do a consistent sampling decisions. For traces, it will mainly use the trace ID. Then we have the other 2 types, which is proportional and equalizing. Both provide specific feature for traces that may already been sampled. If they have not been sampled, then proportional or equalizing would behave the same way by applying at the end a ratio defined in the probabilistic sampling. So proportional. The idea is to reduce the data with a fixed amount. For example, an element that comes sampled with a probability of 30%. If you apply 50% proportional sampling, the element will survive with an end-to-end sampling decision based on 0.3 multiplied by 0.5, which is 0.15, 15%. Equalizing follows a different strategy. After this sampling stage, all the items will have the same overall probability. Let's assume that we want to have only 10% overall sampling probability. An element that has already been pre-sampled with a probability of 50%, we will be sampling it with 20% to achieve the 10% goal. Another element comes with 20% probability, so it will be sampled with the probability of 50%. To again have 10%. So the sampling probability of this stage are chosen based on the previous sampling history of the element. So here is an example of the probabilistic sampler. So we have two probabilistic samplers defined, one for the logs, where we define the field used for the algorithm, and in this case, it's going to be foo, and the sampling probability will be the field in the log. Tail sampling. So tail sampling has the biggest advantage of making decisions with the entire trace, meaning that the OpenTelemetry collector will store all the spans and then apply the sampling decision based on a given rule. Waiting to get the full trace has, of course, a significant consequence. So the collector will have to store all those spans in memory before being able to sample them and then, of course, flush the memory. So using tail sampling will significantly increase the memory usage of the collector. We will touch base on few recommendations when using it in the next chapter. Tail sampling processor allows us to create defined, precise rules to sample only trace having priority flags, for example, trace having errors, trace having response times above a specific threshold, so slow transactions, or apply a probabilistic sampling on trace having a high throughput. So there is plenty of options. So configuring trace sampling is required to configure several parameters related to the processor. So we have the maximum time to wait for the entire trace. So this is going to be decision wait, and it's set by default to 30 seconds. Then we have the maximum number of traces kept in memory, so num traces, that is set to 50,000 traces stored in memory. And we can also configure the cache of this processor, and it has two distinct caches. We have the sample cache and the non-sample cache. We can fine-tune them by defining their size, meaning it will define how many trace ID would be stored in the sample cache or the non-sample cache. By default, this cache is not enabled, and depending on your policy, you will need to define how many traces would be kept or dropped. So if you're planning to sample a small portion of your traffic, you should have a non-sample cache that would be higher than the sample cache size. But the most important thing of tail sampling is defined through the policy field that will hold our sample decision rules. But usually everything that is outside of the policy won't be sampled, and each of the rule of the tail sampling will require to define a name, a type, and last, the settings of the actual type that we have selected. There are several types available. So we have always sample. It is similar to always on, which is meaning 100% of the span sent on that conditions. Then we have latency. This type samples trace based on their duration. So the duration is the time between the first start time and the last end time of our span of our trace. This latency type requires to define at least a threshold in milliseconds, and we also have the options to set a upper threshold to define the maximum value. Then we have probabilistic that samples a percentage of the traces based on a specific probability. So of course, this type will require to define the right percentage. Status code, sample trace based on the status. So we can have different status on our traces. So it could be okay, error, unset. So this is perfect, for example, if we want only to sample 100% of all the trace in error. We have rate limiting that samples trace based on the rate, so this number of spans per second. This is an amazing rule set helping us to control based on the actual volume of a span. So rate limiting will require to set the actual thresholds in terms of spans per second. Span count, so samples the trace based on the minimum and maximum number of spans. If the total number of spans in the trace is outside the specific range, then the trace will not be sampled. This is useful because it helps us to distinguish a trace based on their complexity involving many spans, so you can differentiate those. We have OTTL condition, so this is going to be sampled based on an OTTL, so OpenTelemetry trace language condition that could be applied on a spans or also on a span events. So if you want to learn more about OTTL, check the episode covering it. So I covered that during the episode on OpenTelemetry logs. We have a type which is very powerful. It's AND that allows us to create another rule of policies, and the rules will be applied with the AND, of course, operator. Then we have all the various type of rule allow us to make conditions on the actual span attributes. So the span attributes could be numerical, could be a boolean or a string, so each type will have their own type. We will need to define, of course, the attribute key that will be targeted by the role, and then our role, the conditions will depend on the actual type that we select. So with all these types, we can precisely sample our trace with different conditions. So sampling all the errors, sampling the trace that are considered to be slow, create a probabilistic sampling for specific services, apply a red limit to noisy spans, drop spans that has a health check, and more. For example, I have built the following rule that you can find in the GitHub repo for the tutorial. Here I am applying 1% of probability sampling decisions on the trace generated by the OpenTelemetry collector because it's very noisy. I'm sampling all my errors, and all the live requests of the services are not sampled, and the rest has a probabilistic sampling of 10%. As you can understand, the sampling decision is a very complicated topic. But if you plan to sample, here are few advices. The first one, if you need to apply head sampling, use parent-based sampling to focus on traces part of a long transaction. Use trace ID ratio with cautious because it will impact the statistics or metrics built on our traces. So try to use the probabilistic SAMP processor on the collector that will have less impact, and you can control the statistics at the end. Step 2, use the span metrics only if you know precisely how the spans has been sampled in the SDK level, so on head sampling. Generating metrics on the irrelevant sampling decision will produce metrics that won't be reflecting reality. So use the parent-based sampling decision, and then in the collector, before you start applying any sampling decision, so tail or probabilistic sampling, first produce the metrics with the help of the span metrics connector. Step 3, when sampling in the collector, it does not make sense to combine probabilistic sampler with tail sampling. I mean, tail sampling has the probabilistic sampling as a type when you define your rules. No need. So I will recommend to use tail sampling to make sure you collect a represented portion of the normal traffic, a big portions of all your errors, a big portion of all your slow transactions, all the spans having a priority attribute defined, reduce the spans of a noisy endpoint. But using tail sampling, like mentioned, will consume a significant amount of memory. That is the reason it is crucial to respect the best practices of the collector by always start your trace pipeline with a memory limiter processor, and then end your trace pipeline with a batch processor. Next, we know that sampling will be intensive for the collector. So I would suggest to use several collectors. So one collector receiving all your traces, enriching the traces, and then exporting it using the load balancer exporter that will load balancer the trace based on trace ID. At the end, we want to make sure that all the spans of a given transaction or trace will be sent to the same collector. In terms of observability, the collector produces specific metrics related to sampling. So it will be crucial to keep track on that data. So keep track first on the policy and error with the help of sampling policy evaluation error. Pay attention to the span drop too early. If we reach the limit defined in terms of number of traces or the wait time, the trace would be dropped due to our settings. So meaning that the late spans will be dropped. Look at the following metrics. So hotel call, a processor tail sampling trace dropped too early, that will give you a sign. Then if the span is arriving after the decision wait, then it will be also dropped, but it will be counted in a different counter. So it's going to be counted into sampling trace removal age. The latency to sample our trace is going to be very also important to see how much time we're spending in the collector. So we look at the decision timer latency to see how long it stays in our collector. We can also keep track on the actual rate produced, the sampling rates, but you will need to enable a specific feature flag in the collector to report extra metrics from the collector. So here is the actual feature flag that you need to enable on your collector. Once it's been enabled, you can start creating your ratio with the two metrics. So for example, we are counting all the traces that are actually sampled divided by the total number of traces. So then this will give you the ratio, the sampling ratio applied here. In this example, I'm making a split on the policy, but you can also drop it to also look at the global ratio from a collector perspective. Otherwise, monitoring the memory usage of your sampling collector will be a must. Keep track on our potential memory pressure applied by our sampling decision is going to be required. So look also at the garbage collector, the heap use that is provided by the collector metrics. That's it for today's episode related to sampling. As you can see, sampling is a very difficult point, and defining the right sampling decisions is actual journey. So it's going to be natural to define head sampling because at the end, this is usually when you start implementing the SDK, you think about it, but it will have actually some significant consequences in the data and in the statistics that will be produced based on the traces. So that's why using trace ID ratio, I would say be cautious about it. At least be aware of what type of ratio has been defined, because otherwise you're completely losing control on the statistics produced. I would definitely recommend to do most of the sampling on the collector, even it's going to be more put more pressure on the collector, but use maybe parent-based at the service-based on your SDK level, and then combine with the collector. So if you're planning to do some probabilistic sampling, use it at the collector, because at the end it will respect the consistent algorithm that I mentioned, or otherwise tail sampling will make sure that you will have a good sample of errors or slow traces and everything. So I think tail sampling, it makes completely sense. Again, using tail sampling, like discussed, requires to really observe your collector properly to make sure they are not running into pressure. Otherwise, I'm very excited to see that the community is improving the head sampling. I really hope that consistent sampling will be generalized on all the language and stabilized, so then we can use it and be more confident at the end on the data produced by by any probabilistic sampler that we may apply at the head sampling. So if you enjoyed today's content, don't forget to like and subscribe to the channel. So see you soon for another episode. Bye.